Okay, so welcome back to another class on image processing. Last class, I just introduced the concept of histogram and how histogram is going to represent an image as a 1D plot. And what we noticed in the last class is histogram of an image is a conversion from two dimension to one dimension. Therefore, inverse is not possible, which means if I am giving you the histogram, you cannot get back the original image because multiple images can have the same histogram. So this is what we need to understand. So how this histogram will be useful, or how I can use histogram to represent or to modify an image or enhance an image is what we are going to study, discuss today. Is the slides visible?
Yes, sir.
Okay. So, so what we understood by histogram is it is just a conversion of a two-dimensional image into a one-dimensional plot. So I just look at all the gray levels and how many times each of this gray level is repeat appearing in the image. And just to normalize it, we divide it by the total number of pixels. Thereby, I will get the probability. Loosely speaking, this is probability of occurrence of each of the gray level. Therefore, histogram plot, if I use normalized histogram, can also be called as probability distribution of the gray level values. So this is what we understood in the last class, and we also took some typical examples. So if I am given a histogram of this nature, I should immediately think that it is of a dark image. This is of a bright image because the pixels are crowded towards the brighter region of the gray level. And if it is uh, in fact covering a narrow region in the histogram plot, which means that it is a low contrast image. If it covers the entire region of the range of the gray level values, then we call it as a high contrast image. So what we want is this type of image, not any of this, because this is a dark, this is a bright image, whereas this is a low contrast image. And whenever the illumination is varying, or if you have illumination maybe very less or sometimes very bright, very large illumination, we can expect these type of images to be captured. So how to modify this? There is a way. So as you already understood, if I can convert these type of histograms into an histogram which will occupy the entire dynamic range of the gray level values, so which means it should look like a uniform histogram. So this is one of the processing that we are going to discuss, called histogram equalization. As the name itself says, you are trying to equalize the probability values, which means that you expect all the gray levels to have the same probability of occurrence. Okay. So to discuss this, we need some little mathematics. So I think uh, uh, the equations are simple, so it is easy for you to understand. Let us assume that R is the input gray level of the input image. So now what I am trying to do in histogram equalization is transforming these pixel values into a new pixel value. So I use a transformation function, and whenever R lies in the range of 0 to L minus 1, I expect the range of S to be almost, in fact, the same. So this transformation function, which is trying to equalize the histogram of an image, has to satisfy two conditions, two very important conditions. First one is it should be a monotonically increasing function in the range of 0 to L minus 1. That means it should be something like this, something like this. Okay. So this is also an example. There is a difference between these two. We'll consider it little later. So what is the meaning of this? If you go to any part of this, see, for example, I have some slope here, positive slope. I have a zero slope here. I have a positive slope here. And in fact, in this case, all through it is a positive slope. So nowhere you see that the transformation function is decreasing. That means as R increases, S is not decreasing. So this is what we meant by monotonically increasing function. That means the slope can be constant, or it should increase, or it should be positive. You should not have negative slope anywhere. So that is the meaning of monotonically increasing function. The difference between these two is this is called strictly monotonically increasing. That means in all the places the slope is positive only, whereas in this case we say uh, it is a monotonically increasing function. It is not a strict monotonically increasing function. The reason because in this range you have actually the transformation function constant. That means the slope is 0 here. So positive slope, 0 here, positive slope, whereas here all through it is positive. So that is the difference between a strictly monotonically increasing function and a monotonically increasing function. So what we expect is the transformation function should be monotonically increasing in the range of 0 to L minus 1. Okay. Why this is required? Because there is a need to actually do the inverse. That means I just have made a transformation from R to S. So there is a need for you to go from S to R. So if it is a monotonically increasing function like this, for every input value here, you have a unique different value of the output. Therefore, the inverse is possible. Okay, so that is what is written here. So if I use the inverse function, then it should be strictly monotonically increasing. I cannot expect this. Sorry, I cannot expect multiple values to map single value, because all of you know that if multiple values are mapped to single value, the inverse is not possible. So ideally speaking, we expect this. Okay, so that inverse is possible. The second thing is whenever the input ranges in the range of 0 to L minus 1, the output also should range in the range 0 to L minus 1. That means it should fall in the same range, because you know you are using a particular number of bits for representing the input image. I should be using the same number of bits to represent the output image. For example, if I am using an 8-bit image, I'll have 0 to 255. I cannot expect the transformation to take me from 8-bit to maybe some 10-bit image. So because the representation changes, you cannot uh, change the number of bits. So that is the meaning. For the input range to be in 0 to L minus 1, the output or the transformed pixel should also have the same range. Now, why is condition 1 required? Because if I have this monotonicity, what is the meaning of monotonicity? As I go from darker to brighter region, the output pixels also grow from darker to brighter region. So that is what is the meaning of that. So monotonicity preserves the increasing order from black to white. Otherwise, you know, black will become white and white will become black. That is not expected in any transformation. Okay, that is one of the uh, requirement. And I have already told, the strict monotonicity means it will definitely guarantee you to go back from S to R. That means the inverse is possible. Second condition guarantees that the output levels will have same range as in. That's what I have already told you. If I am using an 8-bit image and trying to transform it into another image by using equalization, my output should also have the same number of bits representation. Okay, so that is the meaning of this graph. I think I have completely explained this. So inverse transformation is denoted by this. That means I'll just use an inverse function to go from S to R. Now, this is actually this slide is in fact will can be better understood if you have taken a course on uh, random processes. I think many of you have completed the elective as random processes. So with that assumption, I'll move on. Now the whole concept here is I have an input image here, and I am just using a transformation to go from one input image to other image. Now, what is expected is in equalization, as the name itself says, the output gray level should have uniform intensity. So, which is something like this. I have an input distribution which is arbitrary, but the output distribution is a uniform distribution. You know, all of you know that uniform distribution means the probability of occurrence of each of the random variable will be same. It is constant. So this is uniform distribution. So if I have this type of distribution, we have already seen that a uniform distribution like this will have a better look of the image. So that is why we want to use equalization. So now, if you look at this problem as a problem of transformation of random variable, as somebody told in the last class, this comes under the heading of transformation of random variable. So I have a random variable R, which is having a PDF probably PR of R. In fact, histogram is loosely called as PDF of the input random variable. So I have a random variable R which PDF PR of R. I'm just trying to do a transformation which takes me from the random variable R to S with a PDF PS of S. Now can somebody tell me in histogram equalization what will be PS of S? What is the name of the output distribution in histogram equalization? Anybody who can respond? I'll show you the graph. So here, from at least from this, you tell me. It is written there. Can somebody respond? Rakesh B, are you there?
Yes, sir.
Yeah. Tell me, I have shown the graph also. What is PS of S? It's written here. I expect you to read it. That's all. Of course, there is a spelling mistake here. It is uniform. Okay. So the output PDF or the transformed PDF should be uniform. That means I expect PS of S to be uniform. Okay. So so if this is looked into as a transformation of random variable, those of you who have taken random processor elective, you know that the output PDF is written as input PDF into dr by ds. Okay, there is a proof for this. For want of time, I am not going to prove it. If somebody is very curious to know how I got this, please let me know. I can explain it separately. But those of you who have done the course on random processes, just refer back to transformation of random variable. We have derived an expression for the output, except that the notations are different there. I hope you remember I used to use capital Fx of x for CDF and small fx of x for PDF. So except that difference, we have derived it. In fact, we have used it and we have solved, and I also showed this as one of the examples. Okay, please refer back. So the output PDF is the input PDF multiplied by dr by ds, and you know r and s are related by an equation, so I need to differentiate it. That is what is required. Now, if I want to have output PDF to be uniform, I need to choose a transformation function here, and if that transformation function is chosen to be a function like this, then I'll have the output to have the PDF uniform. Now carefully look at this equation. I am trying to integrate the input PDF from the minimum 0 because you know gray level values are starting from 0. So 0 to a value R. And if you carefully look at this equation, this is actually the cumulative density function of the input, because you know cumulative density function means you start accumulating the probability values from the minimum towards the value that is required. Okay, so what it tells me is, if you choose the transformation function to be the CDF of the input random variable, then the output PDF will be uniform. I think this we discussed during the course in random processes. So I repeat, if I use the transformation function to be the CDF of the input random variable, my output will have uniform distribution. Okay, so this can be verified also. See, what is the meaning of this? S is equal to this. So suppose if I differentiate this, you know, ds by dr is equal to differential of integration is the value that I have here. So I'll get it as L minus 1 into PR of R. So observe this. Okay. So ds by dr is equal to L minus 1 into PR of R. Simple mathematics. So nothing great here. L minus 1 and to differential of this is PR of R. Okay. Now if I just substitute this in this equation, I want dr by ds. So dr by ds means it is the reciprocal of this. So 1 by L minus 1 into PR of R. So I'll get PR of R into 1 by L minus 1 into PR of R. PR cancels. So I'll get back 1 by L minus 1. And all of you know that that is actually uniform distribution. So this is a proof. The proof here is if I choose the transformation function to be the CDF of the input random variable, the target PDF will be uniform. This is a proof. So any arbitrary PDF can be converted into uniform PDF by taking the transformation to be the CDF of the input random variable. Okay, so please remember this step because we need to solve a problem on this now. So, and I think all of you know how to calculate the CDF of a random variable. So we will just make use of that. So this is the observation. So I need to now choose the input PDF, the transformation function to be the CDF. Now all of you know that even though I am explaining it uh, okay continuous distribution like this, actually your image is a discrete image. So your probability values are discrete because it's a the random variable is discrete. So I cannot have integration, and all of you know the equivalent of integration for discrete values is summation. So let me just look at for discrete values how does it. Please understand these steps because I'm going to solve a problem uh, after a minute. So if I am given a discrete image and you need to calculate the probability values of each of the gray levels, this is all you have to do. Count the number of times each gray level is appearing in the image, divide it by the total number of pixels. Okay, I repeat, count the number of times each gray level is repeating and divide it by the total number of pixels. I'll get probability of occurrence of each of that random variable or each of that pixel. Okay, then you need to do this. I need to calculate this. As I said, this would become now summation. So carefully observe now. So it is summation now. L minus 1 continues to be there. So j equal to 0 to k, where k is a random value starting from 0 to L minus 1. I need to add all the values. So this is cumulative distribution function. All of you know about it. Let us take a problem and solve it okay, after this step. So I will calculate the CDF by using this formula, okay, and use these steps. So these are the steps. Find the probability, find the CDF. Now once I find the CDF, you know this value could be a non-integer value, but gray level values cannot be non-integer. So round the results to obtain the nearest integer. Okay, so you can use either the floor operator or the round operator. It is okay in a gray level, 200 and 201, both of them are same. So either whether I take the lower value or the higher value, I don't have any problem. But let us use some common steps to follow this. Now map the original gray level value to the resulting value obtained in step 3. Okay. So let me now just go to my OneNote and try to solve a problem. So is the OneNote visible?
Yes, sir. Yes, sir.
Okay. So I'm trying to do histogram equalization. Please concentrate because these type of problems are quite common in examinations also, because these are only some typical places where I can actually ask you some problem in this course. So let us now take an example image. I will just take a 6 cross 6 image. Just to make the calculation simpler, I'll just take a 6 cross 6 image. That means I'll have totally 36 pixels, and let me just take a 3-bit image. So if it is a 3-bit image, how many gray level values I can expect? Hello? If it is a 3-bit image, how many gray level values I can expect?
8.
8. So the values could be from 0 to 7. So I'll just take these values. So 0, 0. Randomly I'm just taking 1, 1, 3, 3, 1, 4, 2, 2, 3, 1, 1, 1. Some values I'm just taking randomly. It can be anything actually. 2, 3, 1, 0, 4, 1, 1, 1, 2, 3, 4, 0, 1, 2, 3, 1, 0, 2. So I'll just take these values. Now let us just follow the steps. So as you know, first step is find the probability of the input image, okay, by using this formula. So the first thing I need is nk. That means how many uh, values of each rk exist. So I'll use a table now. So let me just take rk. Rk, you know, you can have 0, 1, 2, 3. As you already told, there will be 8 gray levels starting from 0 to 7. So this table is very important, whatever you are writing now. Okay, so this is rk. Now nk. So can somebody quickly count and keep telling me so that it is easy for me? Count zeros, count ones, count twos. Okay. So what is number of zeros in this image? Quick.
7.
7.
7, sir.
Correct. So there are 7 zeros, and number of ones
13.
13. Very good. Number of twos 7.
7, sir.
6.
7.
Number of 4 is 3, and other values are zeros. Now the cross check is, if I count these values, add all of them, I should get back 36, because this is a 36 cross 36 image. Sorry, 6 cross 6 image. So I will have 36 pixels. So 13 plus 7 is 20 plus 30, 36. Yes, I am correct. Okay. Now this is the first thing. The second one, so the next step is to calculate this probability of RK. Okay. So probability of RK. My suggestion to you is, don't divide and write the decimal values. Okay. Just write it as a rational number like this. So it is 7 by 36, 13 by 36, 7 by 36. This is simple. 6 by 36, 3 by 36, 0 by 36 is 0, 0, 0. Okay. So this is the next step. Now the next step is, go back. So once I do this, find the cumulative distribution based on the probability. So what I'll do is, I'll not use this L minus 1 now. I'll just first do this. PR of Rj, j is equal to 0 to k. I'll do that. Summation PR of Rj, j is equal to 0 to k. Okay. All of you know how to get the cumulative distribution function. So what is this block? Can somebody tell me what is this? CDF. You have done this. What is the first one? CDF. I think the first one is the first value that you have here. What is the second value? Yeah, I thought it is simple. Second value is you have to add this to this, correct? 13 plus 7.
Yes, sir.
Correct. So 20 by 36. Third one, you have to add this with this. So 27 by 36. The 27 plus 6 is 33 by 36. 33 plus 3 is 36 by 36. 36 by 36 is 1. 1 plus 0 is 1. 1 plus 0 is 1. 1 plus 0 is 1. So this is the CDF. All of you know that the maximum value of the CDF will be equal to 1. You cannot have anything above that. Please know that. Okay. So what I have done now is I have just calculated this. But you know, for every value I have to multiply with L minus 1. What is L minus 1 in this case? What is L minus 1 in this case?
7, sir.
Yes, 7. So can somebody tell me what is that value? So I have to multiply this PR of Rj into L minus 1. L minus 1 in my case is 7. So all these values should be multiplied by 7. Now I want you to give the decimal values. I want you to give. Please quick. This into 7, but I want it in decimal. Some of you take calculators and try to do it quickly. Let it be interactive. What is the value?
So 1.36.
Correct. This is 1.36. Okay, what is the next value? Can somebody?
3.889.
Oh, sorry. 3 point?
889.
Okay, so I'll write it as 3.89. Okay, next one.
5.25.
5.25. Very good. Next one.
6.416.
Okay, so I'll do it as 6.42. Next one. 7,
7.
7, 7, 7. Okay, so I hope you understood the steps now. Now what you have to do is just look at the steps now. Okay, look at the steps. I have done this now. Now whatever you have got, round the results to obtain the nearest integer. So let us just round them off, and those will be the output gray level values SK. This will be your SK. Okay. Okay, 1.36. See, you can use different methods. One is just round it to the next integer, that is allowed, or you can use a floor operator. That means just remove the, the decimal value and only retain the integer value. But what my suggestion is, if it is less than 0.5, go to the lowest value. If it is greater than 0.5, go to the highest value. Follow this everywhere. So 1.36 is very close to 1. So it is 1. 3.89. Sorry. 3.89 I will write it as 4. 5.25 I'll write it as 5. 6.42 I'll do it as 6. And this anyway it is an integer. So 777. Is that okay? Is this okay?
Yes, sir.
Okay. So now what you got is round the results. I have got it. So finally map the original gray level value to the resulting value obtained in step 3. So now what you have to do is you have to just map this. Let me just close this OneNote and open it. I am again getting that problem that I had earlier. So sorry for that. I don't think it is getting solved. So okay, let us just move on. Okay, okay, it's not happening. So without wasting time, let me continue. Sometimes this problems. Okay. So what I need to do is, now I have this image. So observe this table now. Observe this table. Okay. So all zeros should be now copied as ones. That is the meaning, right? Sk is this. So all ones should be copied as 4, all twos should be copied as 5, and so on and so forth. So let us now write the output image here. Okay. Okay. So all zeros should be mapped as 1. So 0, this is 0, so this will be 1 and 1. This is your output image. And where else I have zeros? Third row I have zeros here. Fourth row I have 0 here. Fifth row I have a 0 here. Sixth row I have a 0 here. So all zeros are mapped as 1. All ones should be mapped as 4. So this is a 4. This is a 4. All 3 should be mapped as 6. So this will be 6. This will be 6. 1 should be mapped as 4. So this will be 4. 4 is mapped as 7. Look at this table. 4 is mapped as 7. So this will be 7. 2 should be mapped as 5. So this will be 5. This will be 5. 3 should be mapped as 6. 1 should be mapped as 4. I hope you are following what I am just trying to demonstrate here. 2 is 5 and 1 is 4. 2 is 5. 3 is 6. 1 is 4. 3, 1, 0. Then 4 is, this is what? 7. Okay. The last row, 1 is 4. 2 is 5. 3 is 6. 1 is 4. 0. Okay. 2 is 5. So this is the output. Any doubt in this step?
No, sir.
Okay. So let us repeat the steps one by one now. Okay. So what we did is, first we did the probability of the input image. First I counted nk, divided it by the number of pixels. I found the CDF. In fact, first stage is this, then multiplied, rounded the results. Now we are mapping. Okay. So with this, we got the output image. This is actually the equalized image. This is the equalized image, and this is the original image. Now to see what we have done, let us try to plot the histogram of the input image. Okay, histogram of the input image. So you know it will be 0, 1, 2, 3, 4, 5, 6, 7. This would be the input range. What is probability of 0? Can somebody tell me? I think on the table it is available. Probability of 0. 7 by 36, correct?
0.19.
No, I'll just keep it in this only. Or okay, whatever is okay. 7 by 36. Then probability of 1 is 13 by 36. So it is something bigger, but taller. 13 by 36. Probability of 2 is also 7 by 36. And probability of 3 is 6 by 36, slightly shorter, and the last one is 3 by 36, 50% of this, and the remaining are zeros. 5 is 0, probability of 6 is 0, and probability of 7 is 0. This is the input histogram. This is the input histogram. Okay. Now, if you look at this, carefully observe, you don't have the brighter pixels here. Okay, I only have the darker pixels here. So, which means the image is looking slightly darker. That is the meaning. Now, let us plot the output histogram or the target histogram. This is 0, 1, 2, 3, 4, 5, 6, 7. Now, to do this, you have to actually use your output image. Now, how many zeros are there? Quick. No zeros, correct? Am I correct? Are you with me?
Yes.
Okay, no zeros are there, so probability of 0 is 0 in the output image. And how many ones are there? Carefully count. 1, 2, 3, 4, 5, 6 ones are there. Correct? Huh? 6 or 7? 1, 2, 3, 4.
7.
7. Correct. So 7 ones are there. So probability of 1 is 7 by 36. This is actually probability of SK. Okay. Are there any 2's in the output image? No. Just observe no 2's are there. So that means probability of 2 is 0. Are there 3's? No. So probability of 3 is also 0. Number of 4's. How many 4's are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. That's all. I think I have not written one line. Huh?
Yes, sir. Fifth row is missing.
Okay. Somebody should have told me now. Okay. So can somebody quickly tell me? So this is 4. This is also 4. This is 5. And this is 6. And this is 7. This one is 1. Correct? Eh? Am I correct? This is 4.
Yes, sir.
This is 1. Okay. So how many 4's are there? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13 4's are there. So you have probability of 4 as 13. Sorry, 13 by 36. And how many 5's are there? 1, 2, 3, 4, 5, 6 5's are there. 6 or 7. 1, 2, 3, 4, 5, 6, 7. Sorry, 7. So 7 by 36. Number of 6. 1, 2, 3, 4, 5, 6. So 6 by 36. Slightly lesser than this. And number of 7's. 1, 2, 3, 3 7's are there. So 3. Coincidentally, in this case, the values are matching with the input values, but don't uh, think this as the always true. Okay. So this is the output image. Now carefully observe the pixel values are distributed all through from 0 to 7. Whereas in this case, this region, the gray level values are not there. That means your 5, 6, 7 are not there. Bright pixels were missing. Whereas in this case, you can see that, okay, almost all the values are there. Of course, some of them are missing. That is okay, because if one or two of them are missing, neighboring values will not have any effect. So this is the target histogram. So carefully observe. Input histogram is this. The target histogram is this. Ideally speaking, what should I expect? All of you know that ideally speaking, I should have a uniform histogram. This is what is expected. But in a digital image, you cannot expect perfectly uniform, but approximately it looks uniform. Except this, I think almost all of them are of same value, except this and this. Is the problem clearly understood? Because this is a very important problem, and normally expected also to solve such problems. Is it understood? Any doubt? You will be given an image and you are asked to do histogram equalization. So start with this table, keep updating the table, and you will get the target values. So map all the input values to these target values, write the output image, then write the input histogram and the target histogram. Any doubt? Any doubt?
No, sir.
Hello?
No, sir.
Okay, so in the screen you have another, in fact, problem. So here, this is again a 3-bit image. I'll not completely solve it. I'll leave it to you because the slides will be available to you later. But the steps are same. I have just explained it. So I have a 3-bit image, which means I have 8 gray levels. Okay. L minus 1 will be 7 here again. But the only difference is the image is a 64 cross 64 image. In the problem that we just now solved, it is a 6 cross 6 image. So all of you know that I cannot give you a 64 cross 64 image and ask you to count and calculate the probabilities. So when problems like this are given, one step will be avoided to you. That counting will not be expected. So they will not give you the image. They will give you this table itself. Usually they will give you this and this. Sometimes this, but if it is not given also you can calculate. So what is given here is the input gray levels are from 0 to 7. The number of pixels is given here. Okay, since it is 64 cross 64, you will have 64 into 64 pixels. So among them 790 zeros are there, 1023 ones are there, etc, etc. Okay, so this is how the problem is given here. Just to avoid, in fact you cannot print a 64 cross 64 image on sheet of paper and ask you to count. That is why they will give you this table. So one step is avoided here. What is that step? This step is avoided. That means we actually completed this table, but this is avoided here. Okay. So that is the advantage in this case, in this problem. The remaining steps are same. So this is given. Next stage is to find the probability. And you know what is 64 into 64? 64 into 64 is 4096. So you know, if I divide 790 by 4096, 790 divided by 4096, you will actually get 0.19287, etc. So that is this value 0.19. 1023 by 4096 is 0.25. 850 by 4096, etc. Okay. So probability is calculated. Then you need to calculate the cumulative. Okay. So just to explain, S naught is taken here. You know, PR of Rj will be 0.19 itself. So 0.19 into 7, which is equal to 1.33. And similarly, you have to calculate the other values. Okay. So the table is not there. I think you need to complete the table. So I hope you can complete this and compare this, in fact, the distribution function. So this is your SK. Okay. So the table is incomplete here. I repeat, I want you to complete this table and plot the output probability values and just observe what is happening here. Okay. Do you want me to solve this or can you do it?
We will do it, sir.
You will do it, but only let me tell you one important thing here. When I did this problem, what I did is I wrote the target image, and from the target image I calculated these probability values. But let me explain how this can be done without looking at the target image. Okay, so this table will help you. Please learn this, because in the next problem that I am asking you to do, you cannot write the target image and then start counting, because it's a 64 cross 64 image. So once you get this table, now carefully observe. In this case, all zeros are mapped to ones. So which means that probability of 1 is same as probability of 0 in the input image. Am I making the point clear? All zeros are mapped to ones. So probability of 1 is same as probability of 0. Probability of 0 is 7 by 36. Therefore, probability of 1 in the output image is also 7 by 36. That's what you have got here. Is the point clear?
Yes.
Now see, in this is a peculiar case where every input gray level value is mapped to a unique value at the output. But there are places where two of the input gray levels will map to the same output gray level. Let me assume that in this case, let us just make an assumption. Both 3 and 4 in the input image are mapped to say 6. Let us assume this. Both 3 and 4 in the input image are mapped to 6. Now, can you tell me what will be probability of 6 here? It's a simple calculation. If both 3 and 6 are mapped to, 3 and 4 are mapped to 6, what would be the probability of 6 in the output image? Anybody? Is this correct? Hello?
Yes, sir.
Okay, so suppose, see, in this case you don't have such ambiguity, so you are through. For example, probability of 4 is same as probability of 1. Just carefully observe, probability of 4 is 13 by 36. Probability of 1 is 13 by 36. In this case, because every input gray level is mapping to a new gray level. Of course, 5, 6 and 7, all of them are mapped to 7 only, but probability of 5, 6 and 7 in the input image is 0. So you only got 3 by 36. Okay, so so please remember this step, because in the next problem this step is important, because you cannot write the image, you have to look at the table and calculate these probabilities. Probability, suppose if multiple input gray levels are mapped to one unique gray level, you have to for example, in this case, probability of 7 in my case is same as, can somebody tell me what is probability of 7? How many input gray levels are mapped to 7 here? Make it fast.
4,
Just,
sir.
yeah, please. Okay, I think you guys are very indifferent. I cannot help you. So as you can observe, let me not waste my time waiting for you to answer. 4, 5, 6, 7, all the 4 gray levels are mapped to 7. So 4, 5, 6, 7, all of them are mapped to 7. Therefore, probability of 7 should be probability of 4 plus probability of 5 plus probability of 6 plus probability of 7. Now in our case here, if you carefully observe in the input image, probability of 5, 6, 7 is 0. Therefore, it is actually 3 by 36 plus 0 plus 0 plus 0, which will be the final value 3 by 36, which you can observe here. So in this problem, this type of ambiguity is not there, but in the problem that I have just explained to you, in this problem, you will get such a situation. So while finding the output target histogram, you have to carefully look at the input gray levels mapping to the same output gray level, add those probability values and get this. So please verify this problem, in fact solve this problem, because such type of problems are quite common in examinations and tests, of course. Okay, now let us move on. We still have another 2-3 minutes time. Okay, so what you see here is some results of histogram equalization. This is a dark image. When I do equalization, this is what I get, and this is the histogram that I get. Definitely it is not exactly uniform. You cannot expect it to be exactly uniform, but more or less you can say it has a uniform type of distribution. In discrete case, you cannot have exactly uniform because some gray level values doesn't exist at all. So obviously when you do this rounding of business, there is a quite possibility that some gray levels will be more and some gray levels will be less. So that is why it is not uniform. This is a brighter image, and when I equalize it, this is what I get. This is a low contrast image. When I equalize it, this is what I'll get. And of course this is already a good histogram uniform. So that is why even if you perform histogram equalization, I don't think there is any much change because the input itself is good. Okay, so these are the examples, and in fact these are the different transformation functions used for that. I think this concept cannot be explained now. What I'll do is I'll probably go to the MATLAB and maybe demonstrate. Okay, so okay, so let us go to, I think I have already demonstrated this in the previous class, but just to, so let us select this image, and all of you know that this is a low contrast image. Neither I have dark pixels nor I have white pixels. Now I'll plot. So observe here, this is a low contrast image. The gray levels are crowded in between, whereas in this case you have almost all the gray levels. Okay, it's not exactly uniform, but at least you can see that it is having almost all the gray level values. So this is one example. Let me just try it on maybe house image, plot it. Now carefully observe here. This is a very important observation and in fact motivation for the next topic. This is an input image and the histogram looks like this, and as you can see it is having almost all the gray level range here except the dark pixels and the white pixels here. But the image is definitely looking good to you. There is no problem with this image. So for such an image, if I perform equalization, no doubt the output or target histogram looks uniform, but all of you will agree with me that this image is not good. So what does that mean? Histogram equalization is the not solution for everything. I cannot just use histogram equalization wherever okay, I want to do some improvement. So there is no improvement at all. In fact, they spoiled it. Okay, so please remember, histogram equalization is not a solution for everything. Okay, let us also try some other image. Here it's okay, at least some improvement you can see here. Okay, so So the learning now with this is that this histogram equalization always may not yield good result. For example, if I take this type of image and then perform equalization, you are getting this. See, I personally feel that this image is better compared to this because you are getting a dull, washed look in the image. Okay, so what should be done? We will discuss it in the next class.